All right, good afternoon, everyone. Thank you so much for coming to the final COMM 191 review session. It's gonna be fun. We're at UBC Simplified. Basically, our goal is to make a bunch of free and accessible materials and videos to help you review for your final studying, midterm studying, everything like that. We've done a midterm one for this one, and now it's time for the final one. So before we get into what we're gonna be covering today, a few things that were covered in the midterm video, if you can watch, it's on our YouTube video. We're not going to be going over types of data, just the sample type, so like how you're actually sampling people, along with biases, and going more in depth into frequency tables, displaying data. That was done in the midterm video, so if you're wanting to study that, I'd recommend giving that a quick watch. You can scan that QR code, that should be good. We're also not going too in depth into Z tests and hypothesis tests and confidence intervals for Zs, but we'll talk kind of more about that generally. All right, so with that out of the way, let's get into it. Just a few kind of quick reminders that I think came up within the midterm. One thing always keep in mind is that data has to be collected randomly. That's like one of the key important parts, so make sure that it's from a random selected sample. And then the difference between a sample and a population. So the sample is kind of what you take. It's supposed to be a representation of your population. So you have your population, and then you have your sampling frame. And then from that sampling frame, you take your sample, and that's actually what you're collecting the data from. And you use the data collected from your sample to make estimates about your population. So sample goes with estimates and statistic. Population, you're making estimates about the parameter about the population. Another thing to keep in mind is with statistics, we're never actually 100% certain. So you can't say for sure, we can't know 100%. We're making estimates, we're making kind of probabilistic tells, but we'll never actually know for certain. So just watch the wording and some true or false questions of where it says like for sure, absolutely, or we know. Those are pretty giveaway that that's not necessarily true. One thing to keep in mind is when you're comparing different histograms or different graphs, just watch out for the scales. If you see kind of two histograms, they might look very similar, but their scales might be completely off, and that's one way that people who are displaying data can kind of use to trick you, to make it look better than it actually is. So just make sure you pay attention to both the X scale and the Y scale, because if they're different, that means different things within the data. And lastly, just a quick thing is if you're doubling all the data points within kind of a data series, you're also going to double the standard deviation or 4 times the variance because it's 2 squared. A few more, so fences, so this is for determining outliers from the box plots. We talked about that last time, but there's 2 different ones that we want to touch on, so the inner and outer fence. These just come up, so the inner fence would be 1.5 times the interquartile range, IQR, and then the outer one's just going to be 3 times that, so double that. And then if you want to make some estimations about roughly normally distributed data set, if your n is smaller than 30, you take the range, so that's going to be the max minus the min, and you're going to divide that by 4, and if it's above the 30, you're going to divide that by 6, and that'll give you a good estimation for the standard deviation if you don't know much else about it. Another thing for collection of data, if it's not specified that you are taking multiple data sets, so it's not like, oh, we're going to survey these people once a year for 10 years. If that's not specified, assume that it's a cross-sectional collection. So if not specified, like every 6 months we're going to do this, kind of in the initiation of the data collection, just assume cross-sectional. And then we've put in a few formulas there in case you have to estimate the sample size for a study. So you can just plug those in there to kind of help you out a little bit. Okay, so talking a little bit about the distribution between kind of symmetric, unimodal, normally distributed. So here we have all symmetric distributions. So you can see the normal distribution, it is symmetric, and it's also unimodal. So a distribution can be symmetric, but it can not be, that doesn't necessarily mean that it's normal distributed. So here you have this unimodal where the mode, the mean, and the median are all equal to each other, but sometimes the mean and the median can be equal to each other, but there can be different modes. So that's kind of where you have the bimodal distribution there. So make sure you kind of think about what the graph actually looks like and whether or not it's possible to have a mean in the center, but then have 2 modes on the outside when you're getting questions of, what does a distribution look like where the mean, the mode, and the median are all the same. That would be a normal distributed unimodal distribution. And then also you're kind of looking at the variance. So I like to imagine kind of what the graphs look like in terms of the variance. So that's kind of the average distance from the mean there. So just kind of keep these in mind of what is possible, so you are, like, it's able to kind of have a symmetric distribution, bimodal, unimodal. Just kind of keep these pictures in head. Imagine that for any questions that might come up with that. All right, going into regression, we're going to first talk about some terms, then just like the logic of what we use for it, and then kind of going of what we're actually using regression for. So in terms of what type of terms we have, the one thing, probably the most important one, is the slope. So that's your classic y equals mx plus b, right? So that's going to be your m in this case, or they like to call it b1. But essentially, when we're doing regression, we create this line, which is the line of the least squared residuals, sometimes called the best fit line. And this is basically the line which, when you take the residuals, which we'll get to, you add those up, you square them, you add those up. This is the line that has the least squared residuals. So basically, it's trying to be a good predictor of when you get to an x value, you're trying to predict what the y value would be, and you try to be as right on as you can. So the formula for this is you take the correlation coefficient, r, which we'll get to, and then you have the standard deviation of your y sample set divided by your standard deviation of x sample set. And I think it's really important to just keep this formula in mind when they're kind of asking questions or terms about the slope. Just keep that in mind, that this is actually where the slope is coming around. So I like to think about it as how the correlation coefficient is going to determine the direction of the slope, right? So positive, negative. But in terms of the actual like magnitude of the shift, that's going to be dependent on the standard deviation of y, the standard deviation of x. So the correlation coefficient won't actually tell you anything about the magnitude of the switch. It'll only tell you about the direction, because both the standard deviations have to be positive, so that won't have any implications there. So then the intercept, it's created from a formula with the slope, and essentially it's just the intersection of the y-axis there. There's not too much inference to do with the intercept, but I mean, there's the formula there if you ever need to calculate that. Going on to a more complicated one is, so r, so the correlation coefficient, it's essentially measuring the strength of the relationship. And remember, there are no units with r, so if you change the units, you change the scale of your original data set, that's not going to change r. So if you're going from grams to kilograms, meters to kilometers, that's actually not going to change r, because it's just about the correlation between them. And for the correlation, that has to be between two quantitative variables. You can have association, but you can't have correlation between non-quantitative variables. The formula for that, it's a little more complicated. I doubt we're going to have to know or calculate this because we won't be given data sets, but if you ever kind of have to refer back to what r actually is, it has no units because it's made from z-scores, which also have no units. And then, yeah, you square that, and then you get r squared, which is essentially the percentage of y that can be predicted from x. So it's used to kind of determine most of the time, like the strength or how good the model is, but you shouldn't just rely on it. So normally a higher r squared value is better, but that doesn't actually necessarily mean stuff, because you might have overfitting or other things that we're going to get to later. Another thing for r, so that has to be between -1 and 1. Can't be larger than that. If you get 1.2r, that's false. And then for r squared, obviously because you're squaring it, it has to be between 0 and 1. Formula for r squared is r squared, and there's another formula for that coming up later. All right, residuals. One thing to keep in mind, residuals is always going to be the actual value minus the predicted. So residuals, actual is always first. It always goes actual and then minus the predicted. And it's basically, you take this, you square it, you sum it. That's, you take the least of that and you get the best fit line. And again, actual minus predicted. So the predicted is kind of, you take your formula for the line of best fit, and that will be your predicted y value, or y hat. So you're using the formula that includes the slope and the intercept, like the y equals mx plus b there, to get your residuals, and then that's how you get the residuals. And you use the residuals to calculate kind of S sub e, which is essentially the standard deviation of the residuals. standard error of the regression, and basically you're summing up all the square of those residuals and dividing it by some degrees of freedom because you're estimating a few things, and that gives you S sub B, which will be used in later regression. Any questions about regression? Cool. Okay, so just again, the logic is between two quantitative variables. We already covered that. Strength is telling from R, but the magnitude, which is like how much Y will change based on X, that's basically determined by the variation, the standard deviation of Y and X. So that will tell you the magnitude. And then a little bit other things about the outliers. So outliers which are far from the mean will have high leverage, and then if an outlier, when removed, drastically changes the line of best fit, that will be called influential. So it will change the model if it's removed or if it's put back in. And that's kind of just how it can affect the model, whether it's in or not. Other thing is if you increase N a lot, that's not going to change R that much. So if you have sample size of 50 and you have an R of 0.5 and you increase that to sample size of 500, odds are your correlation coefficient is going to actually be the same. And then again, the four-step walk-up. So first, check direction of association, positive, negative. Second thing, check for linearity. We're not doing inference on non-linear variables, so make sure it's like the scatter plot is pretty much in a line. Then you want to check for strength. How strong are they kind of all along the same line, or is it kind of a little bit more randomness? And then anything else. So that's where we're looking at outliers. Maybe they'll influence the line a lot more than we would like. Okay, time to get into some fun stuff. So basically, this is what a lot of the statistics that we do hinges on. So the central limit theorem. First things, you're going to need to have some assumptions about it. So we'll get into what those assumptions are. But if these conditions are true, what it actually is. So with statistics, we are trying to estimate things about a population, but we can't survey an entire population. So what do? We get a sample, which is hopefully representative of that population. And we also know nothing about how that population is distributed. The only thing we know is the things that we collect from our sample, right? So we have our mean of our sample, and then most of the time also we have our standard deviation of our sample. That's the only thing we know. So what can we do with that? Well, we know that if we took another sample, and then another sample, and then another sample, we did a bunch of different surveys of the same thing, of the same population, but it was a bunch of different random samples. What could we tell about that distribution, right? So what we know is that that distribution of taking like 10, 20, 30 different separate samples from the same population, that distribution will look normal. And that distribution will have its centered at the mean of the population. So we know that we take this the distribution of the population, we can kind of model based off of if we took a bunch of different samples, right? A bunch of different means. That would become normal. So it's this thing that if we're able to take 10, 20, 30 samples, then we could model that distribution. But we can't take that many samples. We don't take that many samples. So we make estimates on what that distribution would look like just from the info for one sample. And this is why we use kind of the standard error. That's basically estimating what the standard deviation would be for the population just from our one sample. So kind of visually what that looks like is, we take our one sample, right? We have this kind of very different random distribution. And then what we know from that is we know the standard deviation of the sample, and we also know the mean of the sample. And then if our requirements are true, we're able to use this mean and use this standard deviation to approximate what this so-called sampling distribution would look like. And this sampling distribution is essentially just this imaginary curve of what it would look like if we took a bunch of different samples. So this is trying to, it's like this imaginary thing that we can use because we knew that if we took a bunch more samples, that's what it would look like. But we're only having to take one. And so this sampling distribution, we know to be normally distributed, and we are estimating the standard deviation of the population. So we use the standard error for the most part when we're estimating that, and we get that from the data. So that's how much your estimate will deviate from the actual data set. So it's the sampling distribution itself is kind of this imaginary thing that we construct based on information from our sample. So we take our sample, We have a little bit of information on that, and then we estimate what that would look like if we were to take a bunch of different samples, because it would become normal if our requirements are true, which are one, randomness, and then for binary data sets, that's if NP and NQ are greater than 10, and then quantitative, we have the nearly normal condition, so if your sample size is less than 15, it has to be nearly normal, between 15 and 40. It has to be like no just really strong skewness, and then again for n greater than 40, just has to have like no extreme skewness. And then also the 10% rule, you don't want your sample to be greater than 10% of your population. Okay, little quick thing, so between z-test and t-test, so we use z-test for binary data, so that's when we have kind of P and Q, so like you flip a coin, yes, no, and essentially you're able to get the standard deviation because, or you're able to better approximate the standard deviation through either hypothesis test or a confidence interval because you know the formula for variance for a binary, NPQ, you know that from your p-value, right? So you get one p-value, you can calculate the q-value, and you know your n, so you can better calculate the standard deviation, as opposed to a t-test, where when you kind of just get your mean of your sample, you don't really know much to calculate the standard deviation. So that's why we use standard error. So there are formulas there in terms of kind of when you're calculating a confidence interval, how to get the basically what you're trying to calculate. And then, so the other thing too, for a t-test, this is for quantitative variables. Now, one thing up there, so if you were to know the true standard deviation of the population, you would be able to use a z-test. But we don't know the true standard deviation of the population unless it's given to us. So what we use instead of that symbol up there, which is a Greek symbol, Greek is for population, other letters are for sample. So because we know this, that's the standard deviation. But most of the time, when we get a sample, we won't know this true standard deviation of the population. That's just not kind of how the real world works. So instead, we use little s, which is the standard deviation of the sample. And because we use little s, which is an estimate, we have to use a t-test because we have to account for degrees of freedom. Because we're already estimating one thing, which is we're estimating the standard deviation of the population with the standard deviation of the sample. So that's one thing to keep in mind. That's why we use t-test. And we'll get to kind of what the t-distribution looks like, but we're approximating the standard deviation of the population, that symbol, with little s. So that's why we have to account for a greater, that's why we do n minus 1, because by subtracting 1 from n, you kind of increase the variability. So that's essentially what we're doing there. Okay. So just general confidence intervals. First things first, you'll always have a point estimate. This is almost always going to be the mean that you calculate from your sample. So your p-hat, or your mean from your sample, or just your calculated value from the equation for a line. So you're going to start with that. And then what you want to do is you're going to add and subtract two things. One is going to be your critical value. So depending on what test you do, that will determine your critical value, whether it's one tail, two tail, Z, T, F, Z, T, whatever that is. That'll just be kind of a number. It could be like 1.96, 2.3. That'll depend on your alpha level. So alpha is for a 95% confidence level. Alpha will be 0.05. So alpha plus whatever the confidence interval you're trying to get, those will add up to 1. And so your critical value, you'll be able to calculate that through Excel, or we'll show you some tables of how to do that. And then you multiply that critical value by your standard error, which is an estimate of the standard deviation for the population. And for confidence intervals, you don't actually know what the standard deviation is, so that's why we use standard error. So basically for each different test, there'll be a different formula for standard error. So all you have to do, you get your point estimate, calculate what critical value you need for the alpha level of the test you want to do. You multiply that by the standard error by plugging the numbers into the formula. And then there you have your confidence interval. All right, so kind of general stuff with a hypothesis test, one thing that I like to kind of think about what it's actually doing is, if you go all the way back to z-scores, hypothesis tests are basically just z-scores. Essentially, like, we're standardizing it. So if you think about what you're doing, right, you take your mean, you subtract your null, right? So that's essentially from a z, like, you take your data point, you subtract your mean, and you divide that by the standard deviation or the standard error. And that gives you this number, this test statistic. And if this test statistic is like 10, if our z-score was 10, that means that that data would be very, very, very far away from the mean. It's the same thing here. So we're calculating this test statistic almost like a z-score. We're standardizing it. And we're making inference based on whether or not that test statistic is probable. So a null hypothesis will always be equal to something. So it'll be like the mean is equal to something, or one mean is equal to the other mean. But our alternate hypothesis could either be does not equal, so two-sided, or less than greater than one-sided. And this will depend kind of on the tails. So for t-test, that'll be whether you're including 1, 2 tails, or for z-test, whether you're multiplying the value you get by 2, or leaving it the same. And then the conclusions. So we have kind of the little example there, but once you get your p-value, you compare it to your alpha level, or once you get your test statistic, you compare it to your critical value, which is basically just removing one step, so you don't have to plug more things into Excel. But if your p-value is less than alpha, so if it's less than 0.05, then what you're going to do is you're going to reject the null hypothesis. This basically means that it is improbable that you collected your mean, or you got that proportion, if within the whole population, the null hypothesis is true. So it's super unlikely for you to have collected this data if this hypothesis about the population is true, which means odds are it's not true about the population and something's wrong. So that's what happens when you reject the null hypothesis. If it's not less than or equal to, it's greater than, you fail to reject. Does this prove the null hypothesis? No. You're just failing to reject it. So there might be a question asking, oh, does this prove the null hypothesis if alpha is like 0.9, or the p-value is 0.9? It does not. You're just failing to reject. So just watch the terminology there. And then you have different types of errors, which we covered in the past video, type 2, type 1 errors. All right, so moving on to t-test. So basically, the t-distribution is very similar to the like normal distribution for z-scores, but because we're estimating the standard deviation of the population, we have to account and change it for degrees of freedom. Basically, degrees of freedom, we're minusing n by the amount of estimations we make. So for these tests, we're minusing 1, because we make one estimation about the standard deviation. Now, it's pretty interesting to think about. If your n value got really, really close to infinity, then the t-distribution would approximate and get really close to a normal distribution for z-tests, which is pretty interesting, because then you'd basically you wouldn't have to approximate the standard deviation of the population, because you'd know it. I just kind of like thinking about how it expands out, so that's why it's better to have a larger n, a larger sample. It gives you a better approximation. So that's why we have to use n minus 1 degrees of freedom, is because we're estimating one thing. So because we have kind of lower accuracy when we're estimating stuff, we kind of make the range a little bit wider. And that's kind of what we do there. Any questions about the t-test, t-distribution? Cool. All right. So now we're going to walk through kind of how to do different tests. So we'll have formulas on the board. A lot of them are super similar, so we're going to go through this a little bit quickly. A few things to keep in mind is, for hypothesis test, right, you want to know how many degrees of freedom you're using, and then how to calculate your standard error or your standard deviation, and then also what formula to use in Excel to calculate your critical value, if you're comparing that for a confidence interval. So for a single sample t-test, right, this is just comparing, like, if the mean is equal to one thing, that the true mean of a population is equal to one thing. That's kind of what we're testing here. So the true mean level, like 160 centimeters, is equal to to 100, true mean that we got is equal to 160. So we take our sample mean, what we got, subtract the null hypothesis, what we think that it's equal to, and we divide that by our standard error, which we've been talking about for a little bit. And then depending on if it's your alternative hypothesis is one-sided or two-sided, that'll depend on the type of formula that you use. And if you're calculating kind of that test statistic and you get a really big one, odds are the p-value will be really small. So if you calculate kind of that z-score, so to speak, and your test statistic is really big, it's x there, then your p-value will be really small because that's unlikely, just like how it works with z-scores. And then alternatively, for a confidence interval, use the same standard error that you used for the hypothesis test. All you're doing is for confidence interval for, let's say, 95% confidence interval, right? You're going to have to put in 0.05 into the TIMs, put in your degrees of freedom, you multiply that critical value by your standard error, and then you add that to the mean that you got. That's it. That's it. So it's the same formula for the standard error for hypothesis test, for confidence interval. Just make sure you're calculating properly the critical value, you're multiplying that by the standard error, and then you're adding and subtracting that to your sample mean. That's it. That's the confidence interval. All right, so now we're kind of working our way up to two samples. So for the most part, we're going to assume pooled variance. Pooled variance has to have a standard deviation that can't be more than 2 times the other sample, or 4 times the variance. But we're going to, for the most part, assume this for any questions. And again, degrees of freedom, what are they going to be? Well, it's going to be the number from one of your samples, the sample size from one of your samples, sample size from the other samples, add those together and subtract 2. Why are we subtracting 2? Well, because we're estimating 2 things we're estimating 1 thing from each sample. So this formula looks a little bit complicated, but just plug in some numbers there if you're given that, or sometimes you might just be even given the standard error pooled. But essentially, once you get the kind of standard deviation pooled, what you're seeing here under the square root is essentially you're just averaging out the standard deviation for the pooled data. So you're averaging that out based on n size. So that's why you're kind of adding together the n's and square rooting that. That's to kind of average it out to adjust for if one end is much greater than the other end. It's adjusting for that. So your hypothesis test would be that essentially you're dividing your kind of mean from that. Or for the most time, it's if one mean is equal to the other one. So it'd be 1 minus the other equals 0. So you'll have your combined mean, the subtraction there, and then you'll divide that by your standard error, which is adjusted based on the size of the sample. So moving on to paired t-test. This is when your data must actually be related somehow. So if it's like the same people you survey from now and then 10 years later, even twins or like one company, the same company to different ones, then basically all you have to do is you have to get the combined standard deviation for that kind of those pairs. And the way you do that, remember, you can't add standard deviation, so you have to kind of do that with working through the variance. So square the standard deviation, add those together, and then square root that. And then you're estimating your standard error by dividing it by the square root of n, which is the number of pairs you have. So you have to have the same number of pairs for paired t-test. And oftentimes, again, the null hypothesis for paired is going to be that one equals the other. So you move that over to the other side, and you have the combined mean. So the mean 1 minus the mean 2 equals 0, which is pretty easy in terms of setting up the hypothesis test. And then divide that by the standard error, and that'll give you your test statistic. And then depending on how many tails you have, you can just plug that into Excel, and we'll show some formulas for that as well. So paired must actually be pairs in tau, and it's essentially the same thing as a single sample t-test, just with the combined standard deviation. A little bit more complicated unequal variance. The formula for the standard error is really simple. Again, kind of same idea in terms of the math here. You're basically averaging out the standard deviation, or the variances here, based on sample size. So if one sample size is a lot bigger, it's going to kind of differ. It's averaging it out to make the combined variance there, or the combined standard error more accurate. And then in terms of degree of freedom, it's super complicated formula, so we don't need to know that. Just assume the smaller degrees of freedom. So whichever n is smaller, just assume a smaller degree of freedom from there. But odds are we won't need to know how to calculate those degrees of freedom, and it's the same, pretty similar to the pooled variance in terms of the setup that the null hypothesis would be that one mean equals the other. And then lastly, kind of talking about z-test. So we did one of these before in the past video, but one thing to kind of keep in mind, so for normal hypothesis test, when we just have kind of if our mean parameter, if our population parameter, sorry, equals a number, we use that parameter to calculate our standard deviation. But since for a two-sample z-test, our null hypothesis is going to be that like one p, like this p hat equals the other p hat, like that's equal to each other, we can't actually use that. Like we don't have as much certainty, so that's why it'll be standard error. So it'll be standard error that we'll be calculating. So because we're using p hat q hat, it's not actually the standard deviation, it's the standard error. So that should be SE up there. And that's because we don't have like a specific number like how we had in the past of like, oh, we think the proportion of the parameter of the population is equal to 0.6. Since we don't have that, since it's just kind of the two proportions equal to each other, we have to use the standard error. But the setup of the test is still the same. So what you'll do is you'll take kind of if you're doing a difference, right, you'll take the one mean minus the other mean, and then if you're comparing that to something, but for most time it'll be null hypothesis is if this mean is equal to this mean. You'll move it over to the other side, so you'll have the combined mean, and you can just subtract those, and then you have to combine for the standard error, which is what we're doing here. So again, you can't add standard deviation, so that's why it's all under the square root. That's why we have that formula, and that'll be your standard error that you divide by in order to standardize it to get your test statistic. Okay, so just in order to calculate different critical values, so here are some formulas that basically you can just check, like refer back to during the exam of if you're doing on a one-tail, two-tail z-test, this is what you are putting in to the formula. So just if you have to kind of refer back to, if you don't want to calculate your p-value, just want to leave it at the test statistic, you can just compare back to the critical value. So if you're comparing for a hypothesis test for 95% confidence, you can plug that in there. Or if you want to compare for an alpha level of 0.05, you can also plug that in there. And then rather than having to convert to a p-value, you'll just compare it to the critical value of your test statistic that you calculated. All right, so chi-squared tests, or I like to call them Chi-Chi because it sounds more fun, so we'll call it Chi-Chi. Basically, this is used for count data, which you display through a 100% stacked bar chart. Now, one condition for this is that each expected cell count has to be greater than 5. There are no confidence intervals of this, and Chi-Chi tests are going to be one-sided. The two type of tests that we do with Chi-Chi is basically we're wanting to see if the distribution between data is the same. So this is from different populations, whether or not they have the same distribution. The other null hypothesis that we'll have is whether or not one sample is dependent on the other. So this is from the same population, but it has multiple categorical data. And then, so there's this thing called influence. So basically, if you want to kind of compare standardized how much influence kind of one expected cell or one observed cell had on influencing the result, you take the observed minus the expected, divide that by the square root of the expected, and that'll kind of, whichever one of those is large, has the largest influence, and it can also just kind of tell you the sign of that influence, so whether it's positive influencing or negatively influencing your actual data. So in order to set this up, we'll get all of your observed data in a cells, and then you're going to create a bunch more cells of your expected. What's that going to be? You're going to take the row column of that cell times the column total of that cell, divide that by the total of your data collection. That'll give you your expected. And your degrees of freedom will depend on the amount of columns you have, the amount of rows you have, because we'll have more estimations from there. And then again, for degrees of freedom, why are we subtracting 1? Well, because the column total, we're putting in expected values, but the column total will have to be 1, and then we're putting in expected values, but then the row total will also have to be 1. So that's why we're subtracting 1 to account for that estimation, right? So degrees of freedom is always how many things are we estimating. Here we're estimating the column total. Here we're estimating the row total, because those have to be a specific number. So what do? You're going to take your observed minus your expected, square that and divide it by your respective, and that's going to give you kind of chi squared. It'll be this number, and then all you have to do is plug that into the formula for chi dist and include your degrees of freedom, and then you'll get your p-value. And you can compare that with your specific alpha level. And if you're rejecting the null hypothesis, that pretty much means that it's either different distributions or there's dependence. So depending on, it's the same technique, the same format for each of the different tests, homogeneity or dependence, but it's just different conclusions. Any questions on that? Yeah, so similar thing with the influence when you're kind of adding it up. If there's a really large number, let's say like 20 compared to like 2 for each of the cells kind of residuals, that will have a larger influence on it. So maybe, you know, that's something went wrong, or just be aware that that has a larger influence on your data set. Okay. We're going on to inference for regression, which I've been told is going to be a decently big focus. Look at the last 2 assignments for some good review on this. But what are we trying to do? Well, we collect data from a sample, and we want to say, is this useful? Should we maybe take a bigger sample of the same kind of data set? Should we take a different sample to estimate things about the population? We want to see, okay, we took this sample. Is it actually useful in predicting something else? And I kind of like to think about it as like, okay, so if we had a magic 8 ball, right? We're saying, okay, is this magic 8 ball useful at predicting what will actually happen? And if we can say that, yes, it is actually useful, then we can say that, okay, let's collect a bunch of a bunch more magic 8 balls. Let's, we can say that, okay, then it's all magic 8 balls are going to be useful. So if it's not, if the magic 8 ball isn't useful, like if we're testing, okay, from our magic 8 ball that we have, we're testing it, and we conclude that all magic 8 balls aren't going to be useful, well, then we'll try, you know, maybe a crystal ball or something else. So we're basically saying that, okay, we get our slope from our sample, and we want to test whether or not, depending on probability, if this is actually going to be useful in predicting like for the entire population. So whether it's not worthwhile collecting more samples in this kind of same field. So that's kind of the overview of why we do that. Is like, okay, is this sample actually good for predicting stuff? Is this magic 8 ball actually good at predicting stuff, which means we should collect more of them, or should we try something different? One thing to keep in mind is for inference for regression, there's n minus 2 degrees of freedom, because we're estimating 2 things. We're estimating the slope, and we're estimating the intercept. Because we're estimating those 2 things, it's n minus 2 degrees of freedom. So there's 3 different types of inference we can do. One is for kind of the slope. So it's basically just t-testing the slopes, whether or not this slope is actually going to be useful. So most of the time it's comparing the slope to 0. So if a slope is 0, there's no use for it whatsoever for predicting, so it's not useful. So we'll have whether or not the real slope, that's what we're testing, whether or not the real slope is equal to 0, and we use that based on our calculated slope from our sample. So for this, it's the same setup as a hypothesis test. You take your calculated slope, and you subtract, well, most of the time 0, and then you're going to divide that by the standard error for that slope, which has a very complicated formula. So hopefully you won't have to calculate any of that. I doubt you will, but just that'll be the standard error of the slope. There's the formulas there. There's a few different ways for calculating it up. It uses kind of the residuals and the S sub E for that. But essentially, you're just seeing, okay, based on our sample, is this kind of sample slope, like if it's really close to 0, maybe it actually is 0, and we just got lucky that it predicted something, right? So if our sample slope is super close to 0, maybe we just got lucky, and we don't want to conduct a larger sample just based on kind of that luck. So that's why we do this inference for the slope, to actually know if it's useful, if the real slope of all the data within the population is actually useful to predicting something. Very similar to that is that there's confidence intervals. So there's a difference between the confidence interval and the prediction interval. So the confidence interval is you want to try to find the mean value of y at a given x. So confidence interval is for the mean value of y at a given x. So basically your point estimate is just you're going to plug in that value of x into your linear equation. You'll be using a critical value with n minus 2 degrees of freedom, and you'll multiply that by the pre-calculated standard error of the slope. That'll give you your mean, sorry, there's a mistake there. So for the confidence interval, there's a different formula. That'll be up on the slide. So there's a different formula for the confidence interval to the prediction interval. So the only difference between the confidence interval and prediction interval, so for the prediction interval, you're trying to find a particular value of y as opposed to the mean value of y. And there's this really long formula for how to calculate the standard error for that. But for the prediction interval, you just add one more term under the square root. That's the only difference. So the difference between confidence interval for mean value of y is just one, and the prediction interval is just one term. And that makes it a little bit wider confidence interval because, as we know, when you are calculating kind of the mean value of y, odds are you'll be more narrow, you'll be more accurate as opposed to trying to calculate one specific interval or one specific value. You'll need a wider confidence interval. So that's why we add that extra term. And sorry about the formulas on the slide there. Okay. So now moving into multiple regression. So we're talking about 3D, 4D, 5D, 6D, super complicated, space, warp time, whatever it is. Trying to picture what like a 4D thing would look like when you have 4 different predictors. Super complicated. So we have our trusty friend Excel to do it for us, which helps a lot. So we don't have to kind of picture what Einstein would look like or in Interstellar, because that'd be way too complicated. So we don't have to imagine what those super complicated vectors will look like. Okay. So for multiple regression, there are a few different terms that build off of it. This is from the ANOVA table, which probably we'll have to kind of talk about. So we have a few different ones, and then a few different ones kind of calculated based off of that. So SSE, right? Sum of squared errors is the variation that is not explained by the model. Ideally, you want this to be 0. You want everything to be explained by the model. That's not the case. So this is, you see the formula there, right? So that's, again, the sum of squared errors. So we residual, we take the actual minus the predicted, square that, sum that up. This is the variation that is not explained by the model. Contrarily, sum of squared model, or in Excel, I think it's called sum of squared regression. So that's why there's SSR there. This is the variation that is explained by the model, right? So this is our y hat, our predicted value, minus our mean value of y. This is what we want to be large. We want the model to explain all this variance. And we add those two together, and then we get the sum of squared total, which is essentially the variation within the data. And so that's just essentially the value minus the mean, all squared. It's very close to the variance, but we're not dividing it by one thing, and we'll talk about that in a bit. And then the last thing, remember our little friend r squared? Well, now we have a new way to calculate that. So we take the sum of squared model, divide that by sum of squared total. That gives us our r squared. Now, a really good r squared, for the most part, would be 1. And that would mean that sum of squared model equals sum of squared total, right? That divided by that would equal 1. And if that's true, that means our sum of squared errors would be 0, which is good, unless there's overfitting. So you like to think, okay, if our sum of squared models, the closer it is to the value of this SST, the sum of squared total, the smaller SSE is, which means that more variation is being explained by the model, which for the most part means that our model is better. So you can kind of think about that's what actually makes r squared, a higher r squared value, good. Now, you take those and you divide each term by their respective degrees of freedom, and you get a few different terms. So this is like the mean of squared errors. So this is essentially the estimate of the variance of the errors, which are not in the model. And then we also have the average of the variance, which are explained by the model. And then again, if we add those up together, we get what is the variance of y, essentially the variance of y, which is the mean squared total. So if you take the mean of the summed errors, you add that to the mean of the summed squared models, which are explained by the model, you add those together, you get the variance of y. Now, lastly, you take those two terms, so you take mean of squared model, divide that by mean of squared errors, and you'd get the s-stat. And that is basically similar to r squared, kind of shows you how good is the model at capturing all of the variance, right, or capturing what's randomness. So essentially it's how good is the model at capturing the variations as opposed to what's random. So again, if you have a higher MSM, you'll have a higher F-stat, which will mean a lower p-value, which means that odds are your model will be good. Okay, so now we have just what it looks like in Excel. So the top one is actually what comes out of Excel. The bottom one is kind of changed to help a little bit with understanding. So our degrees of freedom, so K, that's the number of predictors we have. So for multiple regression, you could have 4, 5, 6, whatever predictors. That'll be our number K. So that one there, that was just for a simple regression. And then we take that, and then we take N minus K minus 1. That'll give us our second degrees of freedom, and then we add those together. So sum that, so it eliminates the negative K value. That just gives you N minus 1 degrees of freedom. So then just one thing to keep in mind is, so Excel, we'll call it regression and residual. It's the same thing. It's model and then error. So SSM, SS, regression, those are the same thing. So SSM, that's the, we were talking about that. And then again, you can kind of see, so you take the model, you take that SSM, you divide it by its degree of freedom, and that'll give you your MS there. So you take your model, divide it by the degrees of freedom, and that'll give you your mean of squared from the models. And then the last thing is you take this, divide it by this, and then you get your F-stat. So you can refer back to this as kind of how you kind of walk through your starting there with your degrees of freedom, your sum of squared, model errors, totals, and then how you calculate your F-stat from there. And then you take that F-stat, you put it into a formula with different degrees of freedom, and you get your p-value. And for the most part, with hypothesis test for this is if your p-value is less than your significance level, then your model is useful. And we will talk about that right now. So we have two different tests for evaluating a model's usefulness. One is the F-test, big picture. One is the T-test. F-test is like, yo, this model, it's good. It works. But maybe just one predictor variable in that model is actually good, right? So if one predictor, the null hypothesis for an F-test is that none of these predictors are good. So if you fail to reject, right? If you fail to reject the F-test, that means that none of your predictors are good, which is bad. That means you can't predict anything. But if just one of your predictors are actually useful at predicting something about your Y value, then it will pass, you'll reject the null hypothesis. So the null hypothesis for F-test is that none of the predictors are equal, or none of the predictors are equal. The null hypothesis for the F-test is that all of the predictor variable slopes aren't useful, and their slopes are equal to 0. And for this, you'll get kind of your test statistic. You'll use FDist. You'll have two different degrees of freedom. One will be your K, your number of predictors, and the other will be your N minus K minus 1. So just make sure you know kind of the order for those degrees of freedoms, and make sure to include those two degrees of freedom if you have to calculate the p-value from an F statistic. Okay, so that's the big picture, right? You're just testing, okay, is these 10 predictors, is at least one of them useful? Can we use it? The t-test, on the other hand, kind of works more individual. So we're looking for kind of our classes, we're looking at, okay, which one has the highest p-value? Odds are, like it's a p-value of like 0.6. Odds are that's not actually useful, right? Because we're rejecting the null hypothesis of that individual predictor value. We're rejecting that and saying, okay, this means that, or we're failing to reject, so this means that this slope is 0, so it's not useful. So if we have like 10 different predictors, they'll each have specific t-tests, critical values, and then p-values associated with those t-critical values. And we start from removing the largest p-value and then retesting. Remove the largest p-value and then retest until all of our p-values are lower than 0.05, which means that the remaining stuff in the model are all useful. So it's kind of more going individual, one by one, as opposed to the F-test, which is in general. So that's kind of analyzing each predictor's usefulness. And now just be aware that after you kind of take out one predictor variable, the model can change. So p-values of each t-stat can change. So F-test, big picture, general, you're saying, okay, the null hypothesis, none of these are useful. So if you fail to reject that, that means that odds are none of them are useful. If you reject it, at least one of them is useful. That doesn't mean all of them are useful. T-test, you're eliminating predictor variables until what you have left are all useful within that model. Something to keep in mind, so parsimony, simple is good. Odds are you want fewer predictors, so sometimes t-test is better to get these fewer predictors, and that avoids overfitting, which is, oh, you have this perfect model, you perfectly capture, you have so many predictor variables, you can perfectly capture what this y is, but you're overfitting because when you collect a new sample and you try to use that same model, it won't work. Because this model, r squared of 1, is only good for your sample. You're fitting the model to the sample as opposed to getting a model that will be good for all of the population. And we can try to capture this with the adjusted r squared because as we add more predictor terms, r squared can only increase. Or it can't decrease. It can only stay the same or increase. So adjusted r squared tries to kind of adjust with the negatives of adding more n. So it'll give you a little bit more accurate reflection. There's a formula of how to calculate that you can refer back to. And yeah, it's capturing the negative aspect of adding more variables because that's leading to overfitting. And then the last thing is, if there's a large correlation between some of the predictor variables, they can have large swings in their p-values once added or removed. So it can change p-values from like 0.6 to 0.05 or vice versa, depending on whether they're added or removed. So just a few things to keep in mind regarding multiple regression. Okay, last thing here. When we're comparing full versus reduced models, this is a little bit tricky. So the null hypothesis for this one is that the reduced model is just as good as the full one. So if your null hypothesis, if you fail to reject your null hypothesis, that's a good thing in this case. Because basically it's saying your reduced model, your smaller model with less predictor variables, is actually just as good as the full model. And it's kind of like skipping steps between the F and the T's. So it's basically F, you'll have these 10 predictor variables, and you'll say, okay, one of them is good. At least one of them is good. And now rather than having to eliminate one by one, you take, you know, I think these 5 don't work. So you eliminate those 5, and now you have a reduced model. Now you perform the full versus reduced model hypothesis test. And if you reject your null hypothesis, you say, wow, this model is just as good as the full one. Simple is better. Use that smaller model. So basically what you're saying, your null hypothesis is saying the removed variables. So this is Q here. The X variables, the predictor variables that we dropped were useless. Their coefficients were equal to 0. So the ones we dropped, useless. We didn't need them. Our reduced model is just as good. So that's the null hypothesis there. And basically it's kind of skipping steps. So you have your one, you'll perform an F test, you'll be like, wow, okay, one of these variables are good. Now let's eliminate 6 of them. Let's test again. And if it still works, great, amazing. We have a simpler model. We won't overfit. It's perfect. And that's kind of how you kind of work from this large picture with the F test and kind of avoid having to do individual tests on T's just based on like what you assume, what you think. There's a formula for that. So degrees of freedom, we'll have 2. One is Q, which is how many variables you dropped between the full and the reduced model. And then n minus k minus 1, same thing as the f-stat. And then to calculate this new f-stat, which we'll put into the same formula, the f.dist formula there. There's your formula. So you can plug in, so you have your r squared of your full model, your r squared of your reduced model, and you're essentially almost standardizing that again. And just basically plug in the numbers if you're given that. But again, this is for basically skipping a bunch of steps to get rid of what you're doing. And I like to kind of think of it, okay, so if you're given a massive gift, right? Let's say it's Christmas, your birthday, whatever. You're given this massive gift, right? You're like, wow, such a great box. You might get excited, it might be awesome. But it's just this tiny gift card that's in this massive gift box. It would be much simpler, much easier to put that tiny gift card into this small box. And that's essentially what this full versus reduced, what we're trying to calculate with our inference here, right? We're trying to say, okay, yeah, sure, you could put a gift card in this massive box. It works. But it's way simpler, it's way better if we put that gift card into a small model. Simpler, it's better. That's essentially what we're trying to do with these tests. So, you know, it could work. You could still use this big model, but it's extra. It's not needed. And it gets people really excited when they see a massive box and then it's just like a $5 Tim Hortons gift card. Yeah, it's a little sad sometimes. All right, so last thing is we have a little gift for you. We've been working pretty hard on this. Essentially, what it is a flow chart for all the different hypothesis tests. You start at the top, you go through what type of data you have, how many samples you have, everything else, and then it also tells you the formulas of what to use, the degrees of freedom, and then also how to calculate confidence intervals for that. So if we're looking at here, right, if you're using kind of quantitative or categorical data, and you kind of follow it through, it tells you kind of what test to use, paired t-test, like normal t-test, the assumptions that have to hold true, so most of these are the same for all of them, and then what your hypothesis will be, so one mean equal to the other mean, or the parameter equal to something. It'll tell you what to use for your calculation for your standard error or your standard deviation, depending on what formula you're using, what your test statistic will be, so, and then what you put into kind of Excel for the critical value for confidence intervals. And so that is pretty cool. So that is completely for free. You can scan the QR code, access that, download it, keep it for the exam, reference it back if you get in certain data that's asking you what type of data to use. So that, go for it. It should be pretty good. We're happy that came along. Last thing, please scan the QR code, give us feedback for our next forum or our next review session. We're hoping to get an Econ 102 review video out pretty soon, so you can give some suggestions for that as well. So please, it would mean the world to us if you could scan the QR code. But last thing, I just want to thank Reid and Evan up there for helping with the slides, helping film them. If you could give them a massive round of applause, that would be awesome. Beautiful, beautiful. All right, and yeah, so with that out of the way, thank you all so much for coming. Again, check out our Instagram, and we'll be posting this video on YouTube. Instagram will have more materials. Make sure to follow us on Instagram. Follow us on YouTube at UBC Simplified. We're just here to try to help our learning and also try to provide as much free resources to help other people's learning as well. So thank you all so much for coming. We really appreciate it. Thank you, guys.